Okay, Assalamualaikum class and good afternoon. So for today class, we continue with the chapter 5, okay, which is AC power analysis part 1. So in AC power analysis, so this is the topic that cover in chapter 5, which is instantaneous and average power, maximum average power, effective RMS value, apparent and power factor, complex power, and also power factor correction, right? So but for this chapter, we will emphasize more on this last part, okay, because um, actually this part is actually already covered exactly the same in electric circuit 1, right? So therefore we will not go for example, we will not go for any calculation on this part, okay? So what I want you to know is actually to do some revision on what is instantaneous and average power, what is maximum average power transfer, and also effective of RMS or effective or RMS value, all right? But uh, okay, sorry, but we will look at this one, this part, right? Because this part is actually is essential for you to know in order let's say you already learn about AC analysis, which is we cover on Thevenin and Norton theorem. We know in Thevenin and Norton theorem, we need to deliver a maximum power to the load, so therefore our circuit will work proper because we delivered a maximum power to the load, right? So therefore we will look at this, okay, before we go to this part, all right? Okay, so I go straight away. All right, I think this one you can look uh, you can do some revision on this, all right? So you learn this one, I think. You already learned this one. Okay, this is about power. Okay, maybe I will should go some introduction. So power is the most important quantity in electric utilities, electronic and communication system. Each involve transmission of power. So when we say about power, usually it involve a transmission line, right? So you need to deliver a power from source to the load, usually, or in a power system you need to deliver a power from the source, which is from the power generator or power station to the load, let's say, to the houses, right? So this is all these things involve a transmission of power, right? So in industrial and household electrical, power ratings to indicate how much power equip required. For example, you have fan, motor, lamp, pressing iron, TV, and personal computer. Each of these device have their own power rating. So this power rating indicate in these devices. It's actually tell us how much power these equipment require. All right. So exceeding of the power rating can do a permanent damage to an appliances. So kalau if you apply more power to the appliances that more that it can handle, so it can damage that appliances, right? So most common form of electrical power, so usually in Malaysia we have the frequency of the power is 50 or 60 hertz, right? So in Malaysia usually we go for the 60 hertz AC power. So AC allowed high voltage power transmission from the power generating to the plant to the consumer. So mm therefore, in this topic, we will consider our AC analysis or AC circuit, right? We consider an AC circuit for the power analysis. All right. So, as we know, the instantaneous power dissipate in a component is product of the instantaneous voltage and the instantaneous current. So, in a resistive circuit, the voltage and current are in phase. So the calculation is usually very straightforward. right? But in a reactive circuit, so there will normally be some phase shift between your voltage and the current, and the calculating power become more complicated, right? So when we say reactive circuit, so that's mean this circuit involve your inductor and also capacitor, right? So therefore, in this AC analysis, now we involve a complex power, right? So like I said, we not go very detailed in instantaneous power and average power, because you already learned this one in EC1. So but we can look some of it. So when we say instantaneous power, that's mean it's a power at any instant of time. So the rate, or it is the rate at which element absorb energy. So usually the formula for instantaneous power is given by this P of t is equal to V of t and times I of t, right? So that's mean at any instant of time, at t, let's say you are looking for power, instantaneous power, at any time, what is the value of the voltage and current that give you the value of the power, right? So that is instantaneous power. When we say instantaneous power, so it depends on the time. So at any time of instance, so you need to know what is the value of the power. Okay, so we not go this one, right? So I think the explanation is enough. So and then what is average power? So average power is actually average of instantaneous power over one period. So therefore, let's say we are looking for the average value of the power, so that's is actually uh yeah, that's the average power, right? So usually average power is measured in watt, and is let's say uh, um, your when your uh, uh, pace angle between voltage and current are at the same pace, we can say that this power is actually have a resistive load, right? But when your value of theta v minus theta I is at plus minus 90 degree, so we can say that your power is actually a purely reactive load, right? But if your P equal to 0, that's mean the circuit is actually absorb no average power. Okay, so this is average power. That's mean we are looking the average value of the instantaneous power, right? Okay, so a resistive load R absorb power all time, a reactive load L or C absorb zero average power, right? So average power can be said at usually as a real power, right? That's why um, average power is very meaningful in our resistive load. So in reactive load, usually they absorb average power, right? Okay, we not go to the example, right? So then we go straight away to the maximum average power transfer. Alright, so maximum average power transfer. Uh, okay, so you already do the Thevenin and Norton theorem in the previous AC analysis. So we know that in order to achieve a maximum average power, all right, so you need to make sure the value of your uh, load impedance equal to Thevenin impedance, right? So therefore we can say that we can transfer a maximum average power uh, from your supply to the load. But in AC circuit, usually to get the maximum average power that can be transferred to the load, right? So the reactance value for the load must be equal to the negative value of the Thevenin load, and the uh, uh, resistant value of the load must be equal to the uh, uh, resistant value of Thevenin. So that's mean a if this is our Thevenin equivalent circuit, so therefore in order for maximum power transfer happen from your source to the load over here, so your ZL must be equal to the your we can say that ZL must be uh, uh, equal to the complex conjugate of Thevenin impedance. So that's mean a um, and we know that ZL equal to RL plus JXL, and then ZTL equal to RTH plus JXTH. So therefore, in order to maximum power, uh, average power can be transferred to the load, this part must be equal to the negative XTH. So that's mean it cannot be same. Okay, the RTH and RL part must be in the same value, but for the reactance part, okay, so the load value must have a negative value compared to the must have a complex conjugate value for the Thevenin value. So let's say if you this part you got positive 5, so therefore ZL must be negative 5. Hopefully you understand, right? So therefore if this condition is met, so we can calculate the maximum power by using this formula. So which is VTH squared divided by 8 RTH. So therefore we can say we can calculate the maximum power transferred to the load, right? But if the load is purely real, so that means load is actually consists of resistor only. So therefore RL is always equal to ZTH. All right. So therefore, by setting the value of RL equal to RTH and XL equal to negative XTH, so therefore you can use this formula to calculate what is the maximum average power that transfer from the source to the load. Okay. All right, so we go for example over here. So let's say you are given a circuit over here. You need to determine the load impedance ZL. So you need to know what is the ZL value over here that maximize the average power drawn from the following circuit. So therefore, in order to calculate the maximum average power, remember you need to meet this condition, which is your ZL must equal to the uh, complex conjugate conjugate of your ZTH, right? So that's mean you need to calculate the value of ZTH first, and then we make sure ZL equal to the complex conjugate of ZTH. Then we can use the formula over here to calculate what is the maximum power that can be transferred to the load, right? So therefore, if you are given this kind of circuit, so that's mean you need to do, you need to find the Thevenin equivalent circuit. So when we say we need to find the Thevenin equivalent circuit, you need to find what is the VTH and also what is the RTH value for this circuit, right? All right. So therefore, we can start by finding the value of we are using the RTH is actually your ZTH, right? Because we are working in the AC circuit, so therefore we not use R. Instead, we are using impedance, right? So VTH, what the value of VTH and also ZTH, right? So therefore, remember, ZTH Thevenin impedance can be calculated if we turn off all the sources. So in this case, you have a voltage source over here. In order to turn off this voltage source, you need to short circuit this part, right? So therefore, this circuit now become like this. Okay. Okay, now we need to find the value of ZTH. ZTH is impedance, input impedance at the terminal. So the terminal that we are looking, that we are referred to is actually terminal from at the load. So therefore, by looking from this angle, so you can see that this circuit is actually uh, this 4 ohm is actually parallel with the 8 and negative J6 ohm, and then therefore in series with the uh, J5 ohm, right? So therefore ZTH can be calculated by 4 parallel with 8 negative J6 uh, in series with J5 ohm over here. So therefore, by do a calculation, you can get that ZTH equal to 2.933 plus J 4.467 ohm, right? So this is our ZTH value, right? So next, our next step is actually, okay, we know the value of ZTH. Next step, we need to find the value of VTH. So VTH, what is VTH? VTH is actually open circuit voltage at the terminal, right? So this is our uh, cir- open circuit voltage at the terminal. We know that when there is an open circuit here, the current over here is always zero. So therefore, the VTH that we are looking for is actually voltage at this drop at this 8 ohm and negative J6. Therefore, by using a voltage division, right, so we can calculate the value of VTH, which is this voltage over here, sorry, uh, impedance over here divided by total impedance, which is 8 minus J6 divided by total impedance 4 plus 8 minus J6 times with your voltage source, right, which is 10. So therefore, by using your calculator, so you got VTH equal to 7.45 with a degree of negative 10.3 degree volt. Okay. So now we find the value of ZTH and then VTH. Our aim is actually to find the load impedance that maximize the average power. So therefore, we know that in order to find the load impedance, ZLs must always equal to the uh, complex conjugate of ZTH. Okay, ZLs must always equal to the. So therefore, ZTH is RTH plus let's say you got RTH plus JXL. So therefore ZL will always RTH minus JX XL. This is XTH, sorry. Alright. So therefore from here ZL is always equal to the complex conjugate of the ZTH. Alright, so ZTH, we already calculate the value over here. This is our ZTH. So therefore, automatically your ZL should be equal to the complex conjugate of the ZTH. So therefore, it becomes 2.93 negative. Now it's positive. It becomes negative J 0.4 J 4.467 ohm. So therefore, we can calculate the maximum average power by using this formula, right? So this is our VTH value. So VTH squared divided by I at RTH, because this is modulus. So therefore, we just take the magnitude of the value of the VTH. So therefore, 7.454 squared divided by 8. RTH, this is our RTH, which is 2.93. So therefore, P maximum that will be delivered from your source to the load is actually equal to 2.36x watt. All right, so I think you can do this exercise because I already showed the example over here, right? So we know that the key point over here is actually in order to find the maximum average power that being transferred to the load. Always remember your load impedance ZL must be equal to the complex conjugate of the Thevenin, which is ZL must be equal to the ZTH over here, which is RL equal to RTH, and then your XL equal to negative XTH.